Cool, thank you. Ciao a tutti e benvenuti a questa presentazione. So, thank you. Testing on Android devices has always been a chore in my company named Moorline and elsewhere. You know, the device fragmentation makes it impossible to test on each combination of screen size and density, CPU, GPU, and so on. So when you add to that you have very few emulators in your company, very few devices, sorry, in the company, bad emulators, well, you get the picture. That's why I tried to design a virtual device lab in 2013, which I called lubuntu. This lab was never put into production because of network and firewall and software limitations, but this year I'm presenting Poddingue, which is another solution that should make it, hopefully. This solution uses a form of real devices. This will help you to send your Android devices into the cloud, but no, not this way. I've been working for 19 years for a company named Worldline, which is a leader of electronic payment in Europe. So I want to thank Worldline Experts Field and LinuxLab for letting me speak today in front of you. So I want to thank you too for coming for this presentation. So what is it? What is this presentation? It's just a part of my Mr. What If 2018 tour. We are all Mr. and Mrs. What If, but I tend to take as a challenge jokes that colleagues play on me and jokes that I play on myself. Hello, schizophrenia. So the questions I ask myself are, for example, what if you could run Docker Gitlab CI runner or a dependency track Gitlab Enterprise Edition or my ultimate development environment on a useless half a gigabyte machine like Raspberry Pi? So you got it. I love to use things in a way that they were not made for. That's what my tour is all about this year, giving you a taste of my sometimes stupid ideas. Today, I'll introduce you to the fabulous world of SBC through the use of a smartphone device farm that we are using in my company. So back to 2013, we are more and more Android developers in the company needing to test our applications. There were already tools to test, of course, but we had to use the devices plugged directly in our laptop or very slow emulators at that time. So the real devices were hard to book, disappeared sometimes, and were often outdated. There is one time when testing manually on your own phone is not scalable enough, of course. To tell you the truth, it was hell on earth. That's when I got the idea of using Android x86 port to crack Android VirtualBox images on demand and to link them with our integration server process, which was at the time Jenkins. We tried to address as many Android versions as possible and made lots of ROM cooking. The Android debug bridge, which allows to connect your device your laptop to Android devices, was limited at the time to 16 devices binded locally. So we modified the code, and it now had no limit in the number of devices and was able to bind to all IPs. As Google was about to deliver its L version of Android, we named that lubuntu, which is a famous start of the north of France. Unfortunately, it shows a lollipop. As time went by, I had to realize that this proof of concept couldn't make it because of firewall problems and lack of stability of ADB, unfortunately, and other Jenkins limitations. So, with a heavy heart, we abandoned the project. At that time, a Japanese company named Cyber Agent created a product called STF for Smartphone Test Farm. This project aimed at gathering lots of Android devices and plug them into a dedicated server through USB in order to gain control through a web interface. So this was at the time an internal product, so we didn't know about it. But I switched to other tasks, and while they just open sourced it about 3 years ago. But I kept thinking about my first virtual lab because the needs were still there. So, fast forward to last year. I had the opportunity to work again on continuous integration for mobile development and proposed to make a proof of concept. My new colleague, Ibrahim Garbi, had some Mac Mini hanging around, so he's the kind of guy you want to have around you if you're into fancy hardware. So he installed OpenSTF on his Mac, and we started from that. I already told you about my choice of lubuntu in 2013. This time I chose Poddingue as a name. At that time, We didn't know the name Google would choose for its next OS iteration, which is unfortunately Pi and not Poddingue. But why are we still interested now in a virtual lab or a lab? Aren't there a lot of devices available through our company? Aren't emulators much better now? Okay, we still have some devices, but the problem is still we don't know who is using them, how to find them. And in our company, the emulators are a real pain, even if they made great progress. It is linked to our security policy or Windows installation. In fact, each time you launch an emulator, you've got tons and tons of ADB processes that you have to kill one by one until your machine just freezes. So that's the first problem. The second one, even if we had some devices plugged into our laptops or good emulators, how could we link them to our continuous integration system? It would just be usable on our PC, which is not what we need. So our proposal makes a heavy use of this OpenSTF project, but also goes further, and I try to tell you how and why. So F stands for farm. So the first thing to do, maybe the hardest one, is to gather some devices. So you have to convince your manager to buy some devices. Once you've got that, you have to plug them into a USB hub and then link it to a Linux computer running OpenSTF. STF supports Android from 2.3.3 to the latest 9.0. It supports also FireOS, CyanogenMod, and other heavily based Android distributions. So root is not required on the device for any current functionality. You have the remote control of any device directly from within the browser. You have a real-time screen view. You can see the rotation and make the device rotate. The screen, you can type text directly from your laptop into the device. There is a touch support, so you can pinch, rotate, zoom, and so on with a combination of keys and the mouse. You've got really control on your device. The second step is plug it to your integration or to your laptop with the use of ADB. You can use ADB Connect to connect to your remote device, as if it was plugged into your computer, regardless of the ADB mode of the device and whether you are connected to the same network that the device is or not. You can use it in Android Studio or any other IDE you use for your Android development, so you can connect it to your IDE while you are watching the screen on your browser on the second screen, for example. So pretty handy. On this website, you can see which devices are connected to the server, which are offline, unavailable, unauthorized, or unplugged. You can see who is using a device. You can search devices by phone number, EMEI, Android version, operator, product name, or many other queries that you can enter. Powerful queries, but simple to write. You have also the possibility to display a red screen, which flashes when you want to locate physically a device in your huge farm of devices. You can also track the battery level, the health of the device, and so on. So as you can see, the website you get when you install OpenSTF is really interesting when you want to make tests by hand, but that's not really our use case. We want to be able to book a device when our continuous integration process has finished building the application. So, fortunately, there is something in OpenSTF that allows that. It's a simple REST API. So within the web interface, you can create a token to authenticate later on through a curl command, thanks to the REST API. Once you're logged, thanks to this token, you can get some information about the available devices, get information about one of these devices, about the logged user, which happens to be you. You can book a device, and so on, as if you were using the UI. So the typical workflow would be log in, get the list of devices, filter it until you find one that fits your needs, then book it, use it for your test, and then release it for the next user, as you would do with the UI. We have a Python script on Gist that with just two variables, which are the token and the Android version you are looking for, we book a device for you and allow you to launch your test remotely. So you don't have to know where the device is located. For us, it could be at any worldline venue, and for you, it could be just about anywhere. You just ask for it, and you get it. So I'm not a wizard at all. So let me tell you a few things about the architecture of the project. There are several ways to run OpenSTF. Let's start with the local version we used for the proof of concept with the Mac. So for a local installation. You have to install, first of all, Node.js 6.9 or more recent, ADB properly set up, RethinkDB 2.2 or more recent, graphics magics, ZeroMQ libraries installed for communication between the different models, and of course Portobuf for serializing and deserializing data. Also package config so that Node.js can find the libraries. CoreOS is a supported distribution, but any Linux distribution should do the trick. As we had the Mac Mini hanging around, we use this, but it's not a platform that is officially supported because of bugs in the ADB implementation. But for development and tests, that proved being enough. So after installing Homebrew on OS X and later on Linux Brew on Linux, a few dependencies, we had a local OpenSCF server running, pretty easy to do. We then had to be able to access it from anywhere, whatever the building may be. That requirement we weren't able to meet with a previous version of the lab, which was called Libly, was a signature of its death sentence. So we have a solution for that, and we'll see later on how important this is for us. So with our first version of the proof of concept, we were able to reach our server from our office, as it was just next to us, but also from the continuous integration server machines and from any other building of the company. But even if this solution is quite cool, is it our target solution? In fact, not really. It's cool, we've got a server, I can attach to one server up to 49 devices, thanks to several powered USB hubs and USB ports of the machine. But there is no modularity. And what about the failover? We could have to send through the network up to 49 videos of the phone screens. And what about the heat generated in a closed, secure cabinet with batteries waiting to explode because of the heat? Of course, we would have to use a closed, secure cabinet because of the price of the 49 devices. After all, it's maybe not such a good solution, so it's pretty much a recipe for catastrophe. Fortunately, there is another solution supplied by OpenSCF with slave servers hosting the devices and a main server which will work them all. So, to install one slave server or one app server, you have to ensure that your server will be able to handle ZeroMQ, Protobuf, or Docker. So, as you can see, there are lots of services, and it's quite overwhelming. The reason behind that can be found in the name STF. It's farm, so it's distributed naturally enough to be deployed at scale. But don't get stuck on this image, it's unnecessarily complicated. It's just there to show that there are lots of different units that communicate via ZeroMQ. So given this architecture, you can run so-called providers, which are hosts where merely host your devices. So this is the machines where we will plug your Android devices into. This will just run an ADB, Android Debug Bus service called ADB, and a provider service, communicating via ZeroMQ. So at scale, as we did, you will have multiple of these hosts. They will all connect to a so-called app server, which run the other 12 services that make up the STF infrastructure. So this server, the main server, contains several units at the authentication: the RethinkDB proxy, the log service, the storage plugin, the WebSocket, the API, and so on, all communicating via ZeroMQ. So you can distribute these units as you wish, but we chose to use just one server. Now, how does this all play together? So the website is hosted by the main server. If anyone wants to borrow or book a device, he has to log into his account. Once he is logged, he will have access to the list of devices. This list is aggregated by the app server, thanks to all the providers who host devices. The end user doesn't know and doesn't have to know where the device is located. It could be anywhere in the world. It's that simple from the user point of view. So let's have a look now at the workflow and the magic glue that make it possible. So first of all, the device is USB connected and provisioned by the provider, which means that an application called stf.apk is installed. The provider then notifies the app server over the API service on the port 80. The end user can then connect to the web page via nginx service of the app server and choose the device. Then he can connect via ADB from his computer to the dedicated provider that is hosting the device. It is not directly connected to the device, but to him, it looks like he is connected to the real Android device. The app service then negotiates a VNC access to display the screen of the device remotely on WebSocket on the 80 port with a specific protocol which is called minicap. Anyway, so to attain our target, we have used a special VLAN which is in our company office just for special needs. So the machine in this VLAN can be seen from our development laptops, but also from our continuous integration machines, which are Gitlab CI, and even from other laptops in other worldwide venues or countries. So all of this could not be possible if we were using the office network, because of course there are firewalls blocking communication between the buildings, between the countries, and so on. So this VLAN is also available in the server rooms, which means that we can have machines in our office just next to us and communicating with machines in the server room and the other way. That's perfectly what we needed. The app part of OpenSTF could then be hosted on a server room in a virtual machine, and providers could then be just about anywhere in any worldwide venue, as long as we have access to a plug, Ethernet plug linked to this special VLAN. Of course, that's not the case by default. You have to ask to get an access to this special VLAN. It's a security issue, of course. Anyway, we got it, and I'm pretty happy about it. Now, I'm aware that our proposal would make no sense if we don't propose a solution to book devices ahead of time. Let's say a team is happy with the platform as it is, but wants to schedule a test campaign for a whole week. What will happen if they can't get the devices they need when the campaign starts? Of course, a whole week of tests goes to the trash can. So, regarding the authentication, there is a mock-up that you can see, but there is also an LDAP implementation so that it works with our internal authentication system and could work with yours too. Now, as for the booking, nothing has been done yet, but we have to do it soon because people tend to use it quite heavily now, and there are the first conflict happening. So we have to do something to all testers to book some devices for a period of time. When a device is booked ahead of time, we will have to tell the managers of the corresponding provider that they have to reserve them for the people who need it really. So where were we at the time? It's just two variables. You can book a device, use it for your test with your continuous integration process. But sometimes tests can be long, pretty damn long. Fortunately, Spoon, that we already use, is able to do some test sharding, which means that you will be able to use all the devices that you can book to run your test. It will slice the tests into several groups and then run each group on a separate device. This way, your test will be finished way earlier than you would have with just one device. So this is the way we were using test up to now. So there is just one line with Android STF API.py. So if you want to shard the test, you just have to add as many Android STF API as the number of devices you want to book. That's as simple as that. So at that time, our proof concept was working with a Mac Mini under ResX with a special VLAN. But as it's difficult in our company to get some money to buy Android devices, why should we spend that money on some fancy hardware? Furthermore, as I told beforehand, OS X is not a recommended system to use with OpenSTF. So you can always install Linux on Mac Mini, as we did later on, but that makes an expensive Linux box for sure. There comes a NUC. It's a dirt cheap x86 box under 200 euros that could do the job. But where's the fun? And I am cheap, so this is too expensive for me. Here comes a Raspberry. I already had a few Raspi 3B at home. Wasn't. By the way, in the audience, who owns Raspberry Pi? Oh, thank you. Of course, more than 5 million have already been sold, so there had to be somebody with a Raspberry Pi in the room. Thank you. So I had one with a very bad version of Android TV and another one with Lubuntu Mate. On the 3B, not 3B Plus, the network part is not that good. It's only fast Ethernet. But as I had them and not really using them, why not try with them? Now, I thought that not each and every team would be able to buy a Mac Mini or even a NUC, so why not try with that? I did not expect much from it, as it is pretty slow, 1.2 GHz and only 1 GB of RAM, but overall my experience with Ubuntu Mate was quite lame. So that's not the most powerful distro you can have with a Raspberry Pi. However, a few years back I had played with Raspberry Pi 2 and Docker, and more recently I played with Raspberry Pi 0 and Docker and worked too. So with a 3B, I said there was a chance that it could work. So I started with Lubuntu, and after a few tweaks here and there, I was able to install Docker CE on the Pi. I also needed Docker Compose, as OpenSTF orchestrates quite a lot of containers, so you need Docker Compose. Unfortunately, this was not available for Lubuntu, so I had to rebuild it from source with the help of Docker. You have to build locally a Docker image, and then, thanks to this image, you can generate Docker Compose binary. Later on, I started everything from scratch, again, this time installing Raspbian. It was more natural to use it on the Pi, of course, and when in Rome, do like Romans, as they say. It was more performant than Lubuntu Mate, by the way. So the process now was easier for OpenSTF. You just had to install Raspbian, install Docker, install pip, install Docker Compose, thanks to pip. Later on, I discovered another distro called Hypriot OS. The guys behind that distro call themselves the Docker Pirates to express their rebellious and anti-establishment attitude. As most people were only concerned with Docker on big server, they went the opposite direction and chose to use container technology on really small devices. They believe that Docker can be even more useful on small devices than on big servers. I think they are quite right. Hypriot OS is a Debian-based minimal operating system that is optimized to run Docker. It makes it dead easy to run Docker on any Raspberry Pi by just downloading and flashing a prepared SD card. You have just 5 minutes to go before the start of downloading the image to having a running Raspberry Pi with Docker. Then, I thought I had scored a home run. Just launching Docker Compose within the OpenSTF repository would do the trick, wouldn't it? I was wrong. Of course, if Docker image can be executed on any platform running Docker, these platforms have to be for the same processor as the one the image has been built for. Of course, images built for x86 can't execute properly on ARM processors. OpenSTF provides their image hasn't been built for ARM, neither the other images composing it. So I had to rebuild the main image on the Pi because I had some other image, some modifications to make and other images also, the depending images to rebuild. So that was not such a big deal after all. You just have to create a new ARM image based on the Alpine Linux, then reference it in the other images and build and wait and vent quite a lot and wait a long time, and after some time you get your new Docker image. It's pretty cool. I was really happy for 5 minutes until I realized I could not use that on our continuous integration system. All this work around OpenSTF is to make it possible for our users to test their applications within our company continuous integration, continuous development system. So I build my Docker images, my software, everything with that CI. So it's tightly linked, unfortunately, to the x86 architecture. It's not such a good idea to build my images on the Pi. If I can't build them on my CI server either, what can I do? Then I thought, DockerHub had to be able to build my images as the Alpine Linux image I found was there. So I copied my repositories to my GitHub account and was almost sure I would get a fresh ARM Docker image 5 minutes later. Bummer, it did not work. DockerHub is also based on an x86 architecture and can build ARM images. At that time, I just did not get how the Alpine Linux image made it to DockerHub. I then spent some time thinking of using a Pi cluster to build Docker images. I found lots of mighty fine examples and then real ARM servers, which looked perfect until I saw the price tag. I made a little bit of research and I quickly realized that even if you can torture your Raspberry Pi quite a lot, overclock it, make it do heavy computation, it's not such a good idea to put the SD card under a high level of stress. Because with a good heatsink, you can do almost whatever you want with an event and fan. You can do whatever you want with a Pi, but as long as you write often on the SD card, it will kill it someday. You know, you will shorten quite a lot its lifespan. Even just writing log or using swap will kill the SD card one day or the other. So, what could I do? My CI server can't handle building my images, DockerHub can't build them either, and my Raspberry Pi will kill its SD card. I'm stuck. Maybe not. Back in 2013, Resin.io ported Docker to the ARM processor. That's the start of it all. Shortly afterwards, they wanted to offer ARM built to their users. However, ARM servers at that time were not easily available. It was difficult to find such hardware. So they started to look for an emulated solution. Enter QEMU. Of course, you know, QEMU is a wonderful project aimed at emulating other CPU architectures, and it can emulate ARM. So how can this use to emulate a whole container? Since a container can only access its own file system, you have to get the emulator inside the container. This simply means copying the executable in the image that you are trying to build. Unfortunately, you end up with an error not so descriptive, no such file or directory. So what does it mean? Sorry, antivirus want to start now. Oh, anyway. The reason for this error is that QEMU ARM is a dynamically linked x86 binary, of course, which requires lots of other x86 binaries that are not part of this image. So the loader tries to find those binaries but can't find them, so reports no such file or directory. So the easiest way to fix this is to use a statically linked, of course, version of QEMU, which will have no dependencies on its environment. Creating one is just a matter of warping the source code and running configure with ---- static, and after some time you will get the QEMU ARM Linux user QEMU ARM that you will be able to copy once more in your image. So once you have done so, the result is really different. You've got your hello from ARM container, which is a nice first step. There are lots of other steps needed to emulate a whole container, like loading a specific module of the kernel, improving the syntax, and so on. So once all of these steps are done, you are then able to build an ARM image within DockerHub. So that's with that kind of syntax, it's pretty easy. You just have to start with a run crossbuild start, then the standard Docker instruction, and finish by crossbuild end. That's all. So at that time, I felt like I had invented the fire. Later on, our shippable allowed to build ARM Docker images directly from GitHub sources, and of course to push them to DockerHub. So I don't have to destroy my SD card anymore and wait the whole day now in order to build a Docker image for ARM. I can do it on powerful ARM hardware, and best of all, for free. So what do we have now? A working STF provider on the Raspberry Pi with phones connected to it and images built on DockerHub. That's a pretty nice first step in the right direction. Now, down the rabbit hole, the OpenSTF ARM image is not up to date with the OpenSTF x86 image, so another long journey began. Trying to update the ARM image proved quite difficult because the updated versions of the different products composing it, like RethinkDB, Node, NPM, and so on, don't compile right out of the box on the Raspberry Pi or any other ARM hardware. So I opened quite a few issues on the various projects, and I'm still waiting for fixes on several of them. Then, as I had discovered other Linux distros like Ambien or Hypriot, I began to dig and found that the Raspberry 3B was in fact an ARM V8 and not an ARM V7HF, as Raspbian was telling me. All of this was linked to the 32-bit version of Raspbian, which needs to be there because of the big range from Raspberry Pi 0 to Raspberry Pi 3B Plus and now 4. So I had to find something about the ARM history, the ARM v7, v6, v5, v8, v8R, and so on. So I made quite a lot of research on that, and also discovered, by the way, other chip makers and other board makers. So I had to try lots of different cards. It was very too interesting to just ignore. And by the way, I found also gangs of ARM fans building lightly recent Linux kernel for boards that are still shipped with 3.x Linux kernel by their makers. So I also had to try and build my own images for these cards, and I thought these cards, some of them could be useful for my OpenSCF project. But I've been telling you about SBC for quite a long time now. Let me just tell you a few words about that. So as you know it, SBC stands for single board computer, so a computer made of just one board. So they are built around the stock that you know, system or chip, which means that on a single chip you will find the CPU, GPU, RAM, and other chips that are used to control the board hardware like GPIO, USB sensors, LCD, whatever. So GPIO are pretty common on all of these cards. This set of pins allow to communicate with the outside world thanks to sensors, microcontroller cards like Arduino, motors, relays, and so on. They also allow most of the time to plug in some hats, caps, mezzanine, name it if you want. So they are extension cards that will give new features to the board, like having a battery, plugging a hard disk drive, adding more USB port or Ethernet, on a video output standard or audio standard, or just plugging a camera. That's the base of it all, GPIO. So most of the times, these cards will run a version of Linux based on Ubuntu, but lots of them can also run a recent version of Android. Really? This led to another experimentation more on that later on. So lots of these cards are really technology jewels for quite cheap. The downside of it is that the manufacturers don't really care about the code quality or the documentation. So once you have bought them, you are really on your own. Orange Pi manufacturer, for example, makes good SBC for very little money, starting at €9, but the OS they ship with it is pretty lame. Their Android version is based on a very old Linux kernel and is not very stable, and their Linux version is just a shame, almost unusable. When I first got my first Orange Pi 0, this one, the load charge was always at 3, even when being idle for hours. Fortunately, there is a real community of die-hard fans that builds kernels regularly for these boards, and even complete distros like Armian. So I've been able to test some of these cards with recent kernel like 4.14 to 4.19 with some of these boards. So there is also another specificity that makes it difficult to tinker with this board, which is uBooT that you know, and there is a talk this afternoon on this very subject. So it's an open source cross-platform bootloader that provides out-of-the-box support for hundreds of embedded boards and many CPU, including PowerPC, ARM, x86, MIPS, and so on. But if your card is not handled by uBooT, you're stuck. I won't detail it now, but it's almost as if you had to develop your own BIOS for your PC without having the specifications of the card, so it's kind of difficult. So, what we had at that time was OpenSCF running thanks to Docker on a Raspberry Pi and giving access to phones plugged into its USB port. That's pretty nice and cheap, but I had to try with the other boards I had bought. So, if some of them were able to run Android, what if I could use them instead of phones? This would make sense money-wise because they were starting at €9, which is not the price of a phone, and would maybe be better in the long run without batteries, which won't explode or hit. So why not try to make a smoothie with Orange and Raspberry Pi? So comes the one plus from Orange Pi. This board is built on the Allwinner H6. It runs at the same frequency than the Raspberry Pi, and it has the same amount of memory. And as it can handle as OTG, we can connect it on any computer running OpenSCF. So I gave it a good end-user test and hoped that it could be used within OpenSCF. And if it didn't work with Android and OpenSCF, we could always use it as an OpenSCF provider with Linux. Also, I hoped. So I plugged it in OpenSCF provider and waited, and never got any answer. Later on, I looked at the logs and saw that it could not be handled by OpenSCF because of the lack of a touchscreen. So there is an issue opened with Minitouch, and we'll see one day the solution for that. But for the time being, it's out of the picture for being used with Android and OpenSTF. Now, I was back to the rabbit hole. I then thought of using this for an OpenSTF provider, but unfortunately, it was not possible because the kernel is not ready for that. It's not in the mainline yet. So it won't be able to use until a few months for our project. Fortunately, the Orange Pi 0 that I have there is working for an OpenSTF provider. It can handle up to 4 devices. It suffers the same problem that is older brother for Android, so we will have to wait. Sorry, I'm kind of lacking of time. So, in a few months from now, using just an Android Orange Pi 0 plugged onto another Android Pi 0 could be the smallest and the cheapest OpenSTF farm on Earth, but we will have to wait. Sorry about that, I will have to cut it, but there are tons and tons of other SBCs that we could have used, and some of them are really powerful, some of them, sorry. Anyway, I have to stop there. Sorry about that, but I will be there until tomorrow night, so if you have any question of this, or if you want to have the end of this presentation, don't hesitate to get in touch with me. Thank you.